As artificial intelligence drives demand for larger and more powerful semiconductor packages, the industry is beginning a major transition. For decades, advanced chips have relied on organic substrates, specialized materials that connect processors, memory, and high-speed electronics together. But as package sizes continue to increase, those materials face growing physical challenges. One of the most important is warpage. As packages become larger and more complex, thermal stress can cause subtle bending, distortion, and mechanical instability. Even small amounts of warpage can affect manufacturing yield, alignment precision, and long-term reliability. To address these challenges, many semiconductor companies are investigating glass substrates. Glass offers several potential advantages. It is flatter, more dimensionally stable, and better suited for the extremely fine interconnect structures required by next-generation computing systems. Reduced warpage is one of the primary reasons glass is attracting so much attention. But this raises an interesting question. If glass substrates are more stable, how do we measure that stability? Traditional inspection systems are excellent at identifying visible defects. They can detect cracks, scratches, contamination, dimensional errors, and other well-defined anomalies. However, many manufacturing problems begin long before a visible defect appears. Stress fields begin to form, physical instability begins to accumulate, small deviations emerge that may be difficult or impossible for the human eye to recognize. The question becomes not simply whether a defect exists, but whether the physical state of the system is beginning to drift away from its intended condition. This is where Phocoustic's measurement philosophy becomes interesting. Rather than approaching inspection as an image recognition problem, Phocoustic approaches inspection as a measurement problem. The objective is to evaluate physical change relative to a defined reference state. Instead of asking, "What object is this?" the system asks, "How is this physical state changing?" Phocoumetrics extends this measurement-centered approach by treating physical change as a quantifiable state rather than a simple pass-fail defect. Through reference-anchored comparison, directional drift analysis, and persistence-aware evaluation, it seeks to measure how systems evolve, deviate, and maintain conformance over time. In previous demonstrations on this channel, we explored this concept using thin films and semiconductor wafer surfaces. In one experiment, a visually imperceptible thin film disturbance produced measurable distributed drift despite appearing nearly identical to the reference condition. In another demonstration, a semiconductor wafer image containing only a subtle disturbance generated organized directional field behavior that could be measured and visualized through the Phocoustic pipeline. These demonstrations were not focused on finding defects, they were focused on measuring physical change. The same concepts may eventually have applications in advanced semiconductor packaging. Future measurement systems could potentially monitor distributed stress evolution, warpage progression, surface state instability, delamination precursors, and other forms of physical change before they emerge as conventional inspection defects. In that sense, the long-term opportunity may not be defect detection at all. It may be deterministic measurement of physical stability itself. As semiconductor packaging continues its transition toward glass substrates and increasingly complex architectures, new measurement challenges will emerge. For Phocoustic, the question is not simply whether something is defective. The question is whether a system remains in conformance with its intended physical state and how that state evolves over time. That shift in perspective may ultimately prove just as important as the transition from plastic to glass itself.